Morning session, we left off over here, right? So we were trying to understand about the secondary flow patterns, essentially the vortex formations that may impact particle transport and what we can use to develop a reduced model for that. And I hinted at the fact that we can develop some 2D potential flow vortex models with point vortex approximation. Let's move forward from here because we are going to see more of this as we start our simulations next tomorrow. The next thing that I want to cover is related to the mucociliary stream, and it would be a very brief touch on that because we don't include the mucus effect in our modeling yet, and there is a reason for that, and I'm going to discuss that in a moment. But after this, I'm going to show an example with an idealized flow field, which we realized yesterday that if we do try to idealize the geometry for the flow field generation, it probably won't work because we are going to miss all these secondary flow patterns that we just saw that would be possible, that are possible in a flow field. But still, I'm going to show you what happens if we do idealize the geometry while trying to understand the flow field and what the possible differences could mean to a full scale model. So that's the second thing that we are going to do today. So let's first look at the interaction, the mucociliary aspect and the interaction between air and mucus. So I have a printed page in the set for this. Okay, so this is a figure from one of Yao Interval's papers. I did not include the title in here, which I should. I will include that into the lecture notes. So essentially what we are seeing here is the epithelial tissue, which is the base layer. There is a very thin periciliary there, which is very sticky. It sticks to that epithelial surface. The more mobile layer is the gel layer on top. And in terms of the dimension, this is a mean number, of course, 5 and 10 micron. In certain regions, that gel layer could be bigger. So the overall thickness of this could be around 50 microns. So, and the ciliary motion goes on here that helps to slowly move this thing around. And ciliary dynamics is another entirely different sub-area of gel mechanics as we know. So we are not going to get into any of this, but I still wanted to show you what the general profile is like for the mucociliary surface. Now, in our work, since we model the airflow and the particle transport, as I think I have already mentioned, and I definitely did mention during the talk, that the timescale of this mucus motion is much longer than the timescale of the airflow brushing past it. So we don't really need to think about the wall to be a moving wall. We can still think that the wall is static, and that's what we use in the simulations and for that matter in any kind of modeling. But what is interesting is where that particle has landed. So we know that if you remember some of the aspects that I covered during the talk, the targeted deposition at the downwind sites like the lithoperids is quite low. It's typically always below 10%. There could be some exceptions, but yeah, sub 10%. So most of the particles are landing. So if this is the airway, so most of these particles are landing in this region, in the anterior part of the airway. So once they have deposited on the mucus, they are moving with the mucus further downstream. And the target site, let's assume that this is the target site where we have to set, if it's a drug delivery application, that's where we have to set the drug survey. So now, if you think about what is going on the surface here, so I'm looking at the surface from the side. So this is the epithelial tissue. Let's assume that this entire region is this mucus layer. with the cilia over here. At the anterior part, the droplet has landed, or the aerosol has landed. It has some solutes in there, and now it has started to move with the mucociliary string, right? While it does that, these solutes are getting over that mucus film, and probably they're penetrating through the gel there as well. So there is a time scale for that penetration, there is a time scale for the downstream transport. So if the target site where we have to send that drug is, let's imagine that it's here, by the time this drop ends up here and these solutes have managed to percolate, if that matches, then we have targeted drug delivery even without directly depositing those droplets at the target site. So that is one thing. Also, the other open question is if I do manage to directly land the droplet over here, is it sufficient, or are the particulates not going to penetrate through the gel layer of the mucus to the target site, and are we missing the point altogether? These are open questions. There is no work yet on all these things, but something to think about. In terms of the state of art, what people do, they do not think, they think that this is the best possible option to land directly at the target site, fine. But for the anterior deposited droplets, what they do is they don't think too much about the penetration through the mucus. What they track is they unwrap this 3D surface into a 2D domain. So it would look something like this once you unwrap. So basically you're opening up that 3D enclosure onto a 2D plane. So these particulates, they have landed over here, and the mucus is moving like this on the surface, being generated from the goblet cells, and then they track where these particles are going to move with the mucus. So it's a surface, a 2D model, an unwrapped 2D model. So that's what the state of art is. So as you can guess, there are a lot of things that can be done with this. And the good part is the cilia hydrodynamics is a very mature field in fluid mechanics. So there's a lot of work that has been done. One of our common friends, for example, Levan Groto, has done a lot of work on ciliary hydrodynamics. So it is important for us to connect with that community to figure out whether we can use some of their results and put that into this physiologically realistic models. That has not happened yet, truly. Like they have worked on some non-human animals, but not so much in the human systems. Not in a physiologically realistic way. They have idealized the systems a little bit too much as of now. So like the way we are now applying CFD realistically in the human systems, I think it is time that we talk with them, collaborate with them to make sure that it is included.
Like severe sizes are what? Micron size?
If the periciliary layer is 5 micron, the length, max around that. And then the thickness is again finer.
And motion is also around microns per second or something.
I don't know. I have to look up.
The drop which we are making, we are talking about the penetration of particles in the state.
Yeah.
That is not really
No. What I drew over here is no one has worked on that yet. So it is something that to explore. Because think about the solid mechanics through these gel layers. It is a complex enough. It is a non-Newtonian liquid. So it is not trivial, any of that. Yeah. So if any of you get interested in pursuing research on this topic, there is like 20 years worth of things that can be done for the next generation. So I included this picture into the lecture notes. Let me write down some comments before I move to the idealized profit problem. So the air is brushing past this gel layer at the top. So this is interaction. Well, the name of the topic that I've given here is interaction between air and mucus film. I have, so the paper that you read on the first day with from Sani Jan. So with him, we have some collaborations as well to look at drop impact. So what Sani does is basically use glycerol as stand-in for mucus. But then again, it's an approximation, and there is a lot of things that can be done. Okay, so let me write down some comments here. So we have been discussing only about the fluidic motion of air and the flow induced particles within the respiratory tract. But if you do work like this, and if you show it to your community, they will ask, as I was asked during the talk, after the talk, that what about the mucus? So that is a very valid question that you always would get asked. So, however, we do need to remember that the airways are lined with a liquid mucus layer. Now, that statement itself is quite intriguing, because yes, we do know that there is a mucus layer, but do we really know how the thickness varies throughout the domain? We probably don't. We don't, and that is crucial, because what I had assumed in my infection transmission model was this, and that was dictated by that cell paper that came out from UNC, that yes, the ciliated epithelial cells with the ACE2 surface receptor that the virus will bind to is there throughout the entire airway. Why did we assume that nasopharynx is the first hotspot? Because the mucus layer is thinner at the nasopharynx compared to the outer parts of the nose. But did we think a lot about the thickness profile? We did not. We just assumed that it is thinner, and hence, if some droplet directly ends up over there, they would be effective enough at intruding into those cells. So there is some leap of faith going on over here, if you can read between the lines. And there is work that needs to be done in those areas as well.
So no one really knows the thickness profile like along the pathways.
Most
Just
of
assume that 5
like the in vivo data is rare to come by. Like they do a lot of cell culture studies, but that is not in vivo data. And also like how the thickness profile varies between healthy and someone who already has some kind of infection. Okay, so this layer is, let me keep on writing. So this layer is thin, is relatively thin. On the scale of tens of microns. And is usually expected to have little impact on the air mechanics. So that is fine. So we know that for sure that the timescales don't match. So we don't have to worry about that wall effect, moving wall boundary effect on the air flux. But the fact that we are assuming that something depositing directly over there is potent enough for whether it is for drug delivery or it's for targeted infection, that, if you ever write a paper on that, and if you read my papers, I add that as a caveat, as a discussion item. So it is important as mechanicians to understand what are the current limitations in our work. Because most of us here are students, there is this, like many young scientists, they think that what they're doing is end all and be all, but that is not the case. We all have limitations in our work, and it is important to break through those limitations. Okay, so it would have little impact on the air mechanics. The reason being the time scale. Of mucociliary downstream transport is being much longer than the inhaled and, for that matter, exhaled air's motions timescale. Okay, but to this point, I don't have this cartoon on the lecture notes. But let me comment on this and as well. So, however, mucociliary movement in many textbooks or papers, they would call it as mucociliary clearance as well. So mucociliary clearance could be critical for targeted delivery of pharmaceutical solutes that have landed along the anterior parts of the airway. That's a drug delivery application, but the same is true for pathogen embedded particles as well. And maybe at some point I'll get some time to explore this as well. Another thing of that's something to think about for us mechanicians is where this mucus is getting secreted from. So that is something that Dr. Shamant and I have discussed as well while trying to develop realistic models. That is something that we need to know from the biologists, that where the source is, because as fluid mechanicians we know that whatever model we might have, when the source is important, we know for the airflow, of course the source is at the inlet, that's fine. But if it is a biological fluid which is getting secreted, it is not so obvious. And that is something that we have to fight with as well. Anyways, okay, any questions on this? If you get any new ideas on how to approach things like this, you don't have to tell me right now, but I'd be happy to discuss, because these are primarily uncharted waters for most of us.
One comment will be like this is very motions that oscillating.
Yes.
These will be mostly, I guess, in the creeping flow region, or somewhere very low.
Yeah.
On the other hand, there people are like simulating flow over a canopy or like flow over planktons in the seas. Those are again like large scale erosion. Although like they move, I guess they do the oscillation thing,
Yeah.
but the erosion regimes are completely different. So this just reminds me about the flow over planktons or flow over the.
So, what did I look at? So, did you read this paper by James Blake from the 70s? So, when I was.
And write down the name you can read.
Yeah, so, James Blake. So, he wrote a very it was primarily given as a lecture, which was then written verbatim as a paper. So there he posed many open problems. One of them was, if you think about the torus, and you have cilia on top of the torus, on the surface of the torus, and the cilia is beating like this, it can self-propel itself in a Stokes flow. So in a Stokes flow, as we know that motion is reversible, so it is like if you swim in the backstroke, you would go back, so you cannot move forward. So every motion is reversible. But with that kind of ciliary motion, even at
James
low,
Blake or 8%?
8% was on
Because there is something called scallops theorem.
the scallop theorem is by Purcell, but I believe it is
Okay,
James Blake.
okay.
But Purcell's work is also relevant here. Yeah, that is called the scallop theorem, right? That motion thing. So the torus problem was unsolved, and this is I'm talking about 2007 when I was an undergraduate. So I got this JNCSL fellowship, and I worked at IMSC, and that was the problem that I worked on. I could not solve it. Someone else published it after a few years, but yes. Speaking of that, yes, it's a Stokes flow. It's a creeping flow. That's what that application was as well. So that would be a standard approach. Now, whether we can, and I think many of the ciliary hydrodynamics community members, they are using those tools. What they are still not using is, when I go to the DFT, they are using geometries that are idealized, flat plane, spherical. They are not used to using topology that varies regularly. So the geometry equations, they cannot be the ones that
Eric
they're
Robert
using.
opening
Eric
being part of this bacterial motion.
Yeah.
He studied also some South Korean guy, owns Park or something.
Onshun Park. Onshun Park is at Santa Clara. So something to think about how to adopt those tools, and it's a very rich source of tools that they have developed over the last 20, 30 years. How we can bring them into real biohydrodynamics. Okay, so let's move on. And this topic that I'm starting now, and so what is the timeline that we are going to follow? We are going till 4:30 and then?
Yeah, we'll go till 4:30, then 15 minutes break, 4:45 to 5:45 or whatever you feel like.
Yeah.
You can stop at 5:30 also.
Okay, so I will lead beyond 4:30. So we'll have another session as well, of course. So this topic would be for the idealized flow field. I'm going to develop the theoretical formulation, which I think you have seen before as well, hopefully. But then try to solve a problem on that and see what the comparison would be with a full-scale CFD versus this analytical result. So this is, okay, I don't think I have this printout, so let's use this. So this is the idealized modeling of inherent airflow, and this is what I'm measuring. So like a pipe system that we use to study particle transport, we are getting inspired by Sibelius simplification. So this is a curved symmetrical geometry. The flow is driven by that pressure gradient delta P, P1 minus P2. I don't have this as a printout, right? Could you just take in your set? This diagram? No. Once you are done, I will. So this is a curved section. The flow is moving UZ, and the coordinates would be R, theta, Z. So let me draw it out on the screen. So idealized modeling of inhaled airflow. So we have a system like this. the flow would be under the delta P, P1 minus P2, where P1 is on this cross section and P2 is over here, so P1 is greater than P2. The flow velocity is in the z direction, uz, and we are going to use the r theta z system. So this, the central axis, which is not a straight line, which is a curved path, is the z direction, the radial direction. And then if I look at any random cross section on this, so it's a circular cylinder, so we have a circle where the radial direction is like this and theta is measured in this way. So with r theta z, these three coordinates, we should be able to know what is the location of any fluid molecule over here. So theta. And z is, if I look at it like this, z is out of the plane. The other assumptions that I'm going to impose is this is a constant cross section, so if the radius is, let's assume it to be r, it is going to stay constant. When we do the corresponding integrations, we can directly use that value as a constant. So this is the setup that I'm assuming. Let's see what the equations could be. In terms of the constraints in the flow field as such, we are going to assume that it is axisymmetric and steady and Newtonian. Why do I mention this? Because when I first started to use this approach, I was trying to develop a model for blood flow. And with blood, you have the problem that it is probably not Newtonian in certain scales. So I want to make sure that this is Newtonian in nature and axisymmetric and steady. So with this, so we have a steady unidirectional flow and let's now invoke the Navier-Stokes equation. Yes.
Are we assuming that the radius of that channel is sufficiently large to that so that we don't need this whole system?
Say again, the radius of curvature is?
Large enough to limit the radiation because we are using simple coordinates.
Yes.
But the channel is a curve.
No, I'm not enforcing that. I don't think I'm enforcing that. But the z direction, so you are suggesting that if it is basically just a straight pipe. No. Z can change. So the z direction is the EC is changing. Okay?
So then for the fluid and for the particle coordinate system that we see, fluid generally we begin on the framework, right? So we have to fix a particular framework and then analyze.
In the fluid system, there was a different setup. Not like this. It was a pipe, but not like this. So what we had was, we had the theta and the radius. So basically it was the pipe, the theta angle was different, and then we had the radius. There was no z, right? If you remember. And there as well, that if we had taken something in that direction, that would have changed because it was a circular curvature. And it's in here, and the z is changing. Hopefully that would not have that much of a complex impact on the mathematics, but it's not a straight line. Okay. So Navier-Stokes equation, So in the r theta z system, for steady flow, so The dvdt terms are out, so I'm just going to go to the reduced version of this equation, but it is not, it is going to be in the r theta z system. So it is 1 over r del r of r del uz del r plus 1 over r square del 2 uz plus by del theta 2 is equal to 1 over mu del p del z. So if you do the derivation, this is what Navier step would be for in the r theta z coordinates with the time derivative being 0. Now over here, let's see what we can enforce based on the assumptions. So in the assumptions, we have assumed that it is axisymmetric. If that is so, this term is 0. The derivative with respect to theta, that is 0. So we are left with 1 over r del r of r del uz del r is 1 over mu del p del c. Right? Let's put r over here on the other side. Okay, now let's integrate. So integrating with respect to r, we have on the left hand side the del r goes out, so r del uz del r is r square over 2 mu del p del z plus some constant, let's call it a. Okay, and let's call this equation as, we have not named any equation today, so let's call it 1a. Now let's isolate this derivative again. So del uz del r is r over 2 mu del p del z plus a over r. Now what I'm trying to get at is basically a formalism for the flux q for this system. So for which we need to first get the velocity, so we have to do one more layer of integration. So integrating with respect to r again, we have uz as, so there is one r here, so r square over 4 mu del p del z. This is 1 over r, so a natural log of r plus some constant of integration p. So let's call this as equation 2. Now we can evaluate the constants a and b with the boundary conditions. So let's do that. So to compute the integration constants, a b, so the boundary conditions, so we have this as a setup, right? So the boundary conditions, let's figure out what is happening at small r is equal to capital R, so on the walls. So at small r is equal to capital R, we have uz as 0, no slip. So there, here again, the no slip condition is equivalent to assuming that the mucus is not moving. So let's plug that thing back over here. So in equation 2 from this page, we just put this boundary condition. So it becomes uz is 0, small r is capital R, so capital R square over 4 mu del p del z plus a log of r plus b. Let's call this equation 3. we still have those two unknowns intact, A and B. So let's now use the slope of the well-developed, fully developed flow at the center to get one of the constants. So considering a fully developed flow and the resulting slope in the midsection, we have the midsection has smaller 0 because that's how the coordinate system has been set up. So at smaller is equal to 0, we have del uz del z, which is the slope of the velocity at that point, is 0. So this is r, this is the z direction. Now, if the z direction of the unit vectors for z changes, does it matter? It doesn't, because it's a local solution that we are showing with this true all along the midsection. So this is the only point where the z term comes up, and I don't think it matters. So at r is equal to 0, del u z del z is 0, so we had del u z del z in equation 1b over here. So let's plug that thing in. So therefore, in 1b, we have 0, 0 over 2 mu del p del z plus a over r. Now, people raise some issues with a divided by 0, so let's, instead of doing it this way, let's do it in a slightly different way. So let me, from 1b, so from 1b, we can write r del u z del r is equal to r square over 2 mu del p del z is a. And mathematically there is nothing stopping us from doing that. So from 1b we get this, and then we apply the boundary condition for r is equal to 0. So as a result, left hand side becomes 0. This is 0 over 2 mu del p del z plus a. So a is 0. So if a is 0, then we can directly use equation 3 to evaluate the other constant of integration, which is a. So thus in equation 3, we have 0 times equal to r square over 4 mu del p del z plus 0 for a0 is b, or b is minus r square over 4 mu del p del z. So we can now plug this all back into this UZ formalism that we have developed in equation 2, that value for b. So therefore putting a and b in equation 2, we have uz is minus r square over 4 mu del p del z 1 minus small r square over capital R square. And so once we have the uz is the streamwise velocity, we can now integrate this over that entire cross-sectional area of the cycle to get the flux. So integrating this over the entire circular cross-section, we have the flow rate Q is equal to minus pi R4 over 8 mu, and then the del P del C. I'm not showing the intermediate steps, you can do it on your own. Use that UC formalism to cover that entire area. What is the name of this formula?
This user is for positive.
Poiseuille's law, right? This is not the Hagen-Poiseuille, this is the Poiseuille's law, or sometimes called the Hagen-Poiseuille. Anyway, so this is what people use to model flow different. Talking about respiratory system, I know of work from my days as a student at Virginia Tech. They were using this to study how mosquitoes draw blood, the motion through that nectar. Question is how true the assumptions are. Drawing blood to that, is it? Can you assume it is Newtonian, for example? So, but anyway, so this is a very widely used formalism, especially because it is easy to understand. For people who are not fluid mechanicians, they apply this thing a lot. And
Watchtower himself was a thing,
an engineer, right?
some sort of bio-physicist, you can see. Like he was something measuring the blood pressure or some fluid in the blood channels.
Yeah.
So that's like the history of involvement of fluid mechanics in medical science is much more.
Now for blood pressure measurement, like the RBCs are 8 microns, WBCs are 16
Things
microns.
like this, he
You could consider that to be a continuum, but at the mosquito nectar level, I wonder how things happen. Okay, now for the problem that we are going to solve in a while, we I'm not going to use a del P del Z profile. Rather, we are going to use the pressure gradient del P and the del Z, where Z is the going by this particular diagram that I started out with. Z is the total distance that the fluid particle has traveled. So it is a torque path, it is the distance that it has traveled. So that is the delta Z. So delta Z is not really the level difference which at least my students at SDSU often take. Okay, so where are we in terms of time? Okay, so let me write this last thing down as well, although we are not going to need this for the problem that I'm going to solve. So this is the flow rate. The wall shear could be derived as we know tau del mu del u z del r. So Newtonian, so the mu is just mu over here. Now this del u z del r we have already seen from the derivation what that is. So we can directly apply this equation 1b to write what it is. A being 0. So tau omega, tau wall is tau w mu r over 2 mu del p del c. So from equation 1b. Therefore tau w is r over 2 del p del c. So if you think your system is simple enough, you don't want argument for using this. If we convince ourselves that a blood could still be thought of as a continuum, even while the mosquito is drawing it, one argument that works for them is it is a pipe. It is not a respiratory pathway. It does not have those topological deformations. So it's a pipe at a very small scale. And if you come across those systems, yes, why not? You can use this. And all life will be much less complex. Okay, but if we do want to apply this in systems where the geometric complications are there, all lives would become complex because the results would be misleading. So that's what we are going to see in the example. Question?
Yeah, actually, this format for taken for the this was just valid for a straight line.
Yeah.
The moment we introduce the curvature, I think this dp by dz we were writing as del p by del.
And the very basic assumption, the axisymmetry breaks down, right? So that is the main assumption.
I was just thinking like there should be some R term which takes care of the radius of curvature and dash, but that is not.
The art term.
Means which corresponds to the radius of curvature of this angle.
So what you are suggesting is it would be quite different to what we have here. First of all, this theta we cannot play around with it, even for the complex cross sections. But you are right, the R could be played around, but to use R in a fruitful way, we would be stuck at how to set up the boundary conditions. Because we assume that R is constant, that capital R is constant, which it won't be. It would be a function of, say, Z, right? Because as we go further along Z, the R changes. So it would be a function of Z. That means that we are not going to get the constants of integration in this nice format. So it would be a more complex formalism, something to what it's worth thinking about.
So,
Yes.
what is the length of this one? Like if length is 2, what then that
There will be a length given to you in the problem, so the length here is delta Z. So that is the change in Z coordinate along that straight line.
I think we are doing this in the triangle.
Yeah, yeah.
And then it is fine to do this. Because the moment we are in element channel, we have to, I think, take care of that aspect. In the triangle, it is common.
Yeah. So this is just Purcell's law. There was just one Purcell, right? There are many Bernoullis, but just one Purcell.
3, 4 quarters.
Yeah. Okay, so the next thing I should introduce just before we are ready to start the simulations. No, actually, we would need this for the problem. Sorry. Okay, so the next thing that we are going to do is to solve a problem, but to prepare for that, we are at this point trying to generate the flow field in an ideal electricity. That's what we're trying to do, right? So we need to know what kind of flux we are going to simulate. Until now, I have just given you the numbers, right? But since we are also going to run some CFD simulations tomorrow, let me point out how we typically figure out what breathing rate to model. For example, whichever subject you are trying to model the airflow for. So this is guidance for respiratory flow targets. So this comes from the different breathing measurements that have happened over the years. And these are empirical formulas. So we have collected, not us, it started even before I started in this field. So people collected breathing data for males, females in different sitting, walking positions, and then tried to get some kind of statistical trend towards whatever the formulations are. On the other hand, there is a wide body of literature if you are interested on mammalian breathing. So mammals of different sizes, it is possible to derive some kind of power law on what their breathing rates are with respect to their overall body mass. And the same could be true for human beings. So that's what their target was, to figure out some kind of a breathing rate formulation which is a function of the body weight of the person. So that's what I'm going to write down next. So the net as in the flux going in through both the nostrils, which is what we simulate as well. So I don't think anyone asked me yet. It is we are simulating the air going through both the nose. It's not like one is holding one side of the nose. So the net inhalation airflow rate has been formulated as so V dot. Why do I have it as V dot? Think of it as Q. So Q. So I have it as V dot because I was thinking of back when I wrote it, I was thinking of V as the volume equivalent of volume flux. Q is 2.72 W to the power of 0.44 for male subjects, and for females this is 3.78 W to the power of 0.32. So this is data collected when the subjects were sitting with relaxed breathing. And the W is the body weight in kg, and the V dot is the inhalation rate in liters per minute. And this work is from 2009. And Garcia is one of my sort of seniors in the group. I was a postdoc at university. So he's a faculty at Wisconsin now. Anyway, so he collected all these measurements, and this is the empirical formulation that they could achieve. So from then onwards, whenever we are trying to simulate flows where we have to develop something specific for that person, we would use that. As in, we have the body weight data for that person. Many times nowadays, now that I am
For sample, like how many sample size?
like hundreds. Yeah. So statistically, it was, and they have some correction as well. Like this is the simplified version of the foundation. So they have correction on the power, so it is like 0.44 plus minus 0.1 to something like that. But
This like very simplistic relation that it is only dependent upon the body weight.
yeah, and that's what people are trying to get right. So if you think about any mammals, rabbits, dogs, pigs, whales, they have this, they call it the allometrically scaled power law. So allometry means related to the body weight in this case. So that was the idea, like can we get that for human beings as well? Now this is relevant in the sense that if we are trying to develop, so if you're writing a paper for a medical journal, for example, as an engineer, you probably have the data for the person's body weight, the person's gender, etc., etc., and then you generate this very specific flow rate. But if you are writing paper for a fluid mechanics journals, they don't really care. Like if you are modeling 22.78 liters per minute, 20 liters per minute is fine enough. So it depends on the kind of work that you do, but I just wanted to share this with you because the next problem that I'm going to solve would use this formulation, and then we are going to see to generate a similar flow rate or to model a similar flow rate in the idealized system, what difficulties we might come across. So let's stop over here and to continue the next session.
You should contact Ramdev ji and see the what how much